Today we will be discussing how the frequency of the applied signal has an effect on the voltage gain of a BJT amplifier. Because in the last classes what we are discussing about is the analysis of a BJT amplifier, but we were considering that all the capacitances in the amplifier circuit were short circuit. But then this condition is only true for the signal having frequency not very low or not very high, that is in the mid frequency range. But if the frequency of the applied signal is low or high, then the voltage gain of the amplifier will not be the same as we discussed earlier, because then the analysis has to be done taking into consideration the capacitances which are present in the amplifier circuit. Because if we again recall what we were discussing earlier, that the amplifier circuit having capacitances which are coupling capacitors, and these capacitors under DC they are open circuit, and we were considering that under signal being applied or under AC condition these were assumed to have a short circuit condition, because in the frequency at which the signal was applied, at that frequency the capacitive reactance offered by these coupling capacitors were small enough, since we have selected high value of the capacitances, so that effectively we can very well assume that the capacitive reactance is very short or small, and so this is like a short circuit part. So if we revisit the amplifier circuit again, and we will be considering only the common emitter amplifier circuit. So here in the common emitter amplifier circuit, if we look back again, the circuit was having the coupling capacitor C1, C2, and there is emitter bypass capacitor which is C3. Now when the small signal equivalent circuit is drawn considering these capacitors also, then we will be getting a circuit where C1, C2 and CE being the bypass capacitor are there, but apart from these three capacitors we also have other two capacitances which are CBE between base and emitter and CBC between base and collector. Now these two capacitances are coming from the transistor model, because when we were discussing the diodes, if we remember that the diodes are having a diffusion capacitance in the forward bias condition and a transition capacitance which is in the prevalent in the reverse bias condition. Now if we look into the transistor is again having a forward bias diode and a reverse bias diode, the forward bias diode being between the base and emitter junction, and the reverse bias junction is between the collector and base junction. So these capacitances will have to be taken into consideration. That is why the transistor model will be having CBE, that is the diffusion capacitance in the forward biased condition of the diode, which is the emitter base junction, and CBC is the junction capacitance which is in the reverse bias diode between collector and base. Taking this into account and considering all these capacitances which are present in the amplifier circuit, that means the coupling capacitor as well as the emitter bypass capacitor, the whole amplifier circuit will be like this. Now here all the others are simply what we considered earlier, and extra than these are only the capacitances. So now in this circuit we are having the capacitances, so we cannot neglect these capacitances or the effect of these capacitances when the frequency of the applied signal, that is Vs, is not in the mid frequency range. It is either too small or too high. Now what will happen if the signal frequency is in the mid frequency range? What we discussed earlier, let us again go into that discussion. For example, we know the typical values of these capacitances are generally C1 and C2. The coupling capacitances are a few microfarads, and the bypass capacitor, which bypasses the emitter resistance Re, is in tens of microfarads, a bit higher than C1 and C2, but it is in the microfarad range. Now the transistor capacitances CBE and CBC, these two are in the order of picofarads. CBE is typically tens of picofarads and CBC is typically a few picofarads. Now with this concrete example, now let us see the effect of frequency of the applied signal on these values of these reactances offered by these capacitances. For example, we will be taking values of C1 and C2, say 10 microfarad, CE is 100 microfarad, and CBE is in the picofarad range. Let us take 50 picofarad, and CBC is 5 picofarad. With these typical values, now let us find out what will be the reactances offered by these capacitance when the signal frequency is say 1 kilohertz, that is the mid frequency range, means it is neither too small nor too high frequency. Let us take 1 kilohertz being the frequency of the signal which is applied at the input, that is Vs is having a frequency of 1 kilohertz. Now at 1 kilohertz value of frequency, what will be the capacitances offered by each of these, what will be the capacitive reactances offered by each of these capacitance? Let us go to calculate. Now coupling capacitors are offering a capacitive reactance XC1 and XC2 which are equal, because we are taking equal values of C1 and C2, 10 microfarad. So the value of this capacitive reactance will be 1 by, we know that 1 by 2 pi Fc, this is the value of reactance offered by a capacitance. This is omega is 2 pi f, 1 by omega c. We are considering the magnitude. Let us not think about the J part, that means actually it is having actually two components, one is the real and one is the imaginary, but let us take the value of 1 by 2 pi Fc. Now plugging into the values of this C1 and C2 in this expression, C1 and C2 value is 10 microfarad. So 1 by 2 pi, F is 1 kilohertz, so 10 to the power 3 we are bringing in hertz order, and into 10 into 10 to the power minus 6, because it is microfarad. So we calculate this value and it comes to around 15.9 ohm. So this value is quite small value of reactance. Similarly, if we calculate this capacitive reactance offered by the emitter bypass capacitor, that is XCE, similarly calculating 1 by 2 pi into 10 to the power 3 into 100 microfarad it is, so it is 1.59 ohm. So if we look into these values, it is almost like short circuiting the path since these are very small. So these values, as these being very small, we were very legitimate in assuming that the capacitances were like short circuiting when we were considering the amplifier earlier. We were earlier considering that capacitances C1, C2 and CE are such that they are quite large. So in the frequency at which we are considering, we can very conveniently assume them to short circuit the path, and that was what we were doing earlier. And now we are clear that our assumption was not wrong because these values are quite small. We can very conveniently assume them to be short circuiting. Now what about the transistor capacitances which are present? What reactances are they offering? Let us calculate that. 1 by 2 pi into f 10 to the power 3 hertz, and the value of this diffusion capacitance is 50 picofarad. So as picofarad means 10 to the power minus 12 farad. So it is even smaller value in the denominator. So at this frequency of operation, the overall value of this capacitive reactance becomes 3.18 megohm. Similarly, the capacitance in the collector base junction of the transistor, which is XCBC, and that is equal to 1 by 2 pi into 10 to the power 3. 5 picofarad is the value we are taking, which is the typical value. So that comes to 31.8 megohm. If we look into these two values of XCBE and XCBC, that is the reactances offered by the capacitances present in the transistor model, these are very large values and they are in the order of megohms. So effectively these are like open circuit, since if we look back into the circuit, these capacitances are offering such a high value of reactance that they are almost like open circuit, since as the value of these capacitive reactances are very high, they will practically allow no current to flow through them. So as if they are just like open circuit. So that is why that these capacitances were nowhere in picture earlier when we were considering the transistor amplifier in the mid frequency range. So we were having a very simplified circuit without these capacitances. Now if we consider the frequency of the applied signal not at mid frequency or 1 kilohertz range, but at lower frequency. Now when the frequency is low, what will happen to XC1 and XC2, because 1 by 2 pi fc, now this frequency is a smaller value. So if this frequency is small, then the value of XC1 and XC2 will be higher than the earlier mid frequency range. So if we consider low frequency signal, then these capacitive reactances being offered are significantly high. Similarly, this XCE also will be significantly higher now, because this frequency is small, so these values will be high. So XC1, XC2 and XCE, these values will be higher now. If these values are higher, what will happen to the signal in the circuit, because we are now having a considerable reactance in this capacitance as well as this capacitance, all three will be offering considerable significant reactance. So that means there will be a higher drop in the capacitances. So the signal which is applied here will be having a drop here. Similarly, the signal which is available here will be having a drop here. So the output the output signal will be having a lesser value because of these drops occurring at these capacitances. Similarly, the capacitance in the bypassing part of this emitter resistance Re, as this capacitance is no longer short circuit, so it will not be effectively short circuiting, means it will be lesser effective in providing the short circuit part. That is why we will be having a current flow in this resistance Re also, as a result of which the overall voltage gain of this amplifier will be reduced. Since if we remember what is the voltage gain of an amplifier, it is equal to beta times RC parallel RL divided by beta plus 1 Re when this capacitance is short circuiting. But when this capacitance is not short circuiting, then there will be this resistance and this resistance will be coming together in series. So in the denominator of this voltage gain expression, if we have this voltage gain minus beta RC parallel RL divided by beta plus 1, it will be small Re plus capital Re, because this Re is coming in the denominator. So if denominator is now higher, overall voltage gain will be lesser. So due to these two factors, one being that there will be voltage gain, there will be voltage drop here in these two capacitances. So your overall voltage gain, which is the ratio between output voltage and input voltage, or if we consider the overall voltage gain with respect to the signal AVS, it is V naught by Vs. Now this V naught without this capacitance will be higher than V naught with capacitance. Now if there is a capacitance, there will be voltage drop here, so the output voltage what we will be getting is less now. So we will be having a lesser voltage gain. So voltage gain reduces when the signal frequency is low. Now the other capacitances which are present in the transistor because of this diffusion and transition capacitances, this cannot affect because the overall capacitance or the capacitive reactance offered by these capacitances, as it is 1 by 2 pi Fc. Now frequency is smaller, so the reactance will be even higher. So it will be even higher than the mid frequency range. So if this capacitive reactance is even higher, that means they are more and more like open circuit, and they will not be coming into the picture because the current cannot flow through these two capacitances. So in the low frequencies, the parameters which are going to affect the voltage gain are the capacitances C1, C2 and Ce, that is the coupling capacitors and the bypass capacitor. Now let us consider the high frequency region. At high frequencies, what will happen is that the transistor capacitances CBE and CBC will offer a lesser reactance, because now the frequency is higher. This frequency is higher means the capacitive reactance will be now decreasing. Earlier it was like open circuit very high, now it will be decreasing. Now when the capacitive reactance is decreasing, now it will be allowing more and more current to flow. That means a part of the current will be now flowing through the diffusion as well as the transition capacitances, and the effect is that they will be shunting away a part of the current IB, because if we look into the circuit again, there are these two capacitances. Now the current coming into this point, to the base point, without these two capacitance, this current would have flown through this resistance beta plus 1 Re, but now because a part of the current is being shunted away by this CBC and CBE, because their capacitive reactances are now low. Earlier it was almost like open circuit, very high, in the order of meg ohm it was reactance. So it was not possible for current to flow through them, but now a part of the base current will be shunted away by these two capacitances, because they are offering lesser and lesser reactance. As a result of which, the base current, what would have been there had there not been these capacitances present, is now less. So base current is less means collector current is also less, beta times IB, it will be less. So if the collector current less, that means what? The voltage gain will be now again lesser, because the voltage gain will be depending upon the output voltage by input voltage. Now output voltage is the current through this resistance RL multiplied by this resistance RL, and this current is coming from this current source, which is the dependent current source, beta times IB. Now if IB is less, then this dependent current source is providing less current, so that means this current will also be less, so overall voltage gain will be less. Now from this analysis we have seen that the frequency when it is low as well as when the frequency is high, in both the cases we will be getting the voltage gain of the amplifier being lowered. So we cannot ignore the effect of frequency of the signal being applied at the input on the overall voltage gain of the amplifier. So today we will be discussing the frequency response of an amplifier, means we will be analyzing how the gain is reduced with frequency being low or frequency being high. And once again, here at high frequencies the coupling and bypass capacitors will not affect, because if the frequency is higher, then their values will be smaller and smaller. It will be more and more short circuiting type, because of this fact that it is 1 by 2 pi fc. Now if f is high, the overall capacitance offered by this coupling as well as bypass capacitors will be lesser and lesser, and that does not harm our voltage gain. So if we consider low frequency, the capacitances which will be responsible for the lowering of the voltage gain are C1, C2 and Ce, and when we consider high frequency of the signal, the capacitances which will be responsible for lowering of the overall voltage gain of the amplifier are the junction capacitances of the transistor, those are CBC and CBE. So we can very conveniently divide our analysis into two parts. One is when the frequency is low, that is at low frequency, and then at high frequency we can consider the response of the amplifier separately. So that is what we are going to do now. So if we now plot the voltage gain of an amplifier versus frequency, we get a curve like this. Now if we focus on this curve in the mid frequency range, that is when the flat portion of the curve we get. That is, we are plotting this gain versus frequency. So frequency is varied from 0 onwards, and in the y axis we are plotting this voltage gain AVS. Now AVS, customarily it is that voltage gain with respect to the source, that is AVS is V0 by Vs, overall gain of the amplifier. with respect to the signal being applied, and within bracket f is written because we are now considering the gain as a function of frequency. That is why the parameter or the argument inside the bracket will be f. Now the plot, if it is plotted, that gain is plotted versus frequency, then during this portion mid frequency the voltage gain is constant, which is denoted by A naught. A naught is the mid frequency voltage gain. That is the same voltage gain which we were discussing, taking into account the capacitors C1, C2 and CE being short. Now if the frequency is lowered, we will be getting the voltage gain being drooping off, that is, it is going to be lesser and lesser, as well as when frequency is higher, then also the gain will be lowering from the value of A naught as seen here, and the lowering of the gain occurs because of the reasons just now being explained. Now one point to be noted in this graph is that we are marking two frequencies, FL and FU. FL and FU are called cutoff frequencies, where the gain of the amplifier drops off to 1 by root 2 times the gain of the mid frequency region. That is 1 by root 2 means 0.707. So the values of the frequencies at which the gain drops off to 0.707 times of the constant gain A naught, which is obtained at mid frequency range, are called cutoff frequencies. Basically one is lower cutoff frequency, one is upper cutoff frequency. That is, lower cutoff frequency is the cutoff frequency in the low frequency region, and upper cutoff frequency is the cutoff frequency in the higher frequency region. Now what is the significance of this 0.707 or 1 by root 2 times? It comes actually from practical considerations, because generally when we apply an amplifier for audio purposes, if it is an audio amplifier, practically what happens is that even if the gain of the audio amplifier, even if it drops off to up to 1 by root 2 times the gain, then also our ears are not able to percept that change in the gain, and we hear almost same gain, or we hear the audio signal as having the same amplification. That means there is no distortion perceived by the ears. So our ears are naturally immune to the audio signal gain being dropped off to maximum of 0.707 times the peak value, and from that considerations actually this 1 by root 2 times or 0.707 times, that value has a particular significance. So we consider that even if the voltage gain drops up to that level, still it is tolerable, and that is why this distance between the upper cutoff frequency and lower cutoff frequency is called the bandwidth, 3 dB bandwidth. So 3 dB bandwidth, where it comes from, again that has to be seen. We are writing it decibel, and this is a particular unit which is obtained from a ratio and taking its logarithm to the base 10 multiplied by 20. That is 20 log of to the base 10 of the ratio between the gain and the gain at mid frequency, as is shown here. This 20 log 10 magnitude of AVSF to A naught, that value is in dB unit, and this is customarily done to normalize this AVSF gain with respect to the value of gain A naught, and then express this magnitude of frequency response in dB, and that is done practically in the books. Also we see that the plot is in dB, that is in decibel. So that decibel unit we have to take in this way. So if we consider the voltage gain in the mid frequency range as AVS which is conventionally that V naught by Vs. Now in the mid frequency means where there is no effect of frequency of the signal, this is a constant, and that value is given, if we recall our earlier analysis, it is minus Rin by Rin plus Rx into beta times of RC parallel RL divided by beta plus 1 small re. So this we are familiar with from our earlier analysis. So this is the overall gain of the amplifier in the mid frequency range, because it is not having any frequency component, it is constant. Now as we have shown in the plot, the lower frequency cutoff and the upper frequency cutoff or higher frequency cutoff are two frequencies, and we can find out basically from these two frequencies what will be the value of lower cutoff frequency and what will be the value of upper cutoff frequency for a particular amplifier given the parameter values, because we know that at those frequencies the value of the voltage gain will be 1 by root 2 times or 0.707 times the value in a mid frequency range, that is this value. So as it is customary to write it in decibel, so at the in decibel scale if we write, then at FL and FU, that is at the lower cutoff and upper cutoff frequencies, the value of the voltage gain AVS F, this value, a magnitude of this value will be 1 by root 2 times of A naught. So now if we put that, then we will be getting 20 log 10 of AVSF is 0.707 times A naught by A naught, and this value is the dB value. If we calculate this, A naught cancel, 20 log 10 of 0.707 becomes minus 3. So the overall quantity becomes minus 3 dB. So that is why this minus 3 dB is very important as far as amplifiers are concerned. This is the bandwidth, and that signifies the distance between the lower cutoff and upper cutoff frequencies, because at those frequencies the gain becomes 1 by root 2 times the maximum gain, which is A naught. So now this is the dB scale minus 3 dB bandwidth we are going to find out. What will be the lower cutoff frequency and upper cutoff frequency, that we are going to find out, which are known as 3 dB cutoff frequencies. So 3 dB cutoff frequencies means immediately we know that the gain has reduced to 1 by root 2 times of A naught. So using this analysis we can now proceed to find out what is the lower cutoff frequency. So now when considering the lower frequency region, the capacitances which will be there will be C1, C2 and Ce. Now in order to find out the lower cutoff frequency, what we will be doing is that we will be considering each capacitance separately, like we will be considering C1 and neglect the other two, and similarly for the others also we will be doing like that, and find out the lower cutoff frequency due to each of the capacitances, and finally we will be finding out the overall lower cutoff frequency considering all the three. So let us first find out the lower cutoff frequency due to C1. Now other two are short circuited, we are assuming, that is C2 and Ce will be short circuited and C1 is a significant capacitance. So now the circuit of the amplifier will be having C1 and there will be no other capacitances. Now if we look into this circuit, which is very familiar to us because earlier also we were discussing in the mid frequency region the same circuit, only in that case this C1 was not there. Now if we find out what will be the input resistance of this amplifier, input resistance Rin can be found out by looking into the input circuit at the terminals AB. So Rin is nothing but these two resistances in parallel, that is RB parallel beta plus 1 RE. Now if I consider this Rin and consider the circuit to the left of Rin, we get this circuit where we can see that the input voltage Vi is across this Rin, which is equal to Vs into Rin by Rin plus this whole series impedance, and that is nothing but Rs plus 1 by j omega C1. Simplifying this expression a little further, we get Vi equal to Vs into Rin by Rin plus Rs plus 1 by j omega C1 can be written as, rationalizing by multiplying numerator and denominator both by j, we get in the numerator j will come and in the denominator j square. We know j square is equal to minus 1. So minus j by omega C1, and again omega we know it is 2 pi f C1 for this circuit. Just replacing this, I get the expression of this ratio of Vi by Vs equal to Rin by Rin plus Rs minus j into 1 by 2 pi f C1, where f is the frequency at which we are operating the input signal. That can be further reduced to another expression by writing as a common Rin plus Rs, taking this common in the denominator, it will be 1 minus j into 1 by 2 pi f into Rin plus Rs into C1. So that can be further written as Rin by Rin plus Rs into 1 by 1 minus j. I write 1 by 2 pi f Rin plus Rs whole term is in the numerator, and in the denominator keeping this into C1 in the numerator and keeping only f in the denominator. This f is in the denominator only. I can write this one as this one. Now just look into this term 1 by 2 pi into Rin plus Rs into C1. That term, let us write it as FLC1, because this is 2 pi into a resistance into a capacitance. So RC basically is nothing but a time constant of the circuit, and that intention we are keeping in mind. So we are expressing FLC1 as 1 by 2 pi into Rin plus Rs into C1. Now if we consider only the magnitude of this ratio, because you see that there is a j term, so the angle as well as magnitude both are associated with this. But forgetting about the angle, because we are interested in finding out the overall voltage gain, which is having the magnitude of the voltage gain. So we are writing only the amplitude or magnitude Vi by Vs, that is equal to Rin by Rin plus Rs into 1 by, taking the magnitude of this part, it is a complex quantity of 1 minus j theta suppose. So if I want to find out the magnitude of this component, this whole expression, it will be 1 plus theta square under root. So that is what is done, 1 plus FLC1 by f whole square under root, means to the power half. Now this is the ratio between Vi and Vs. Now at frequency f is equal to FLC1, when the frequency becomes the frequency FLC1, the value Vit by Vst, this magnitude or amplitude of this ratio becomes Rin by Rs plus Rin into 1 by, when these two are equal it will be 1. So 1 by 1 plus 1 means 2, square into half will go. So it will be in the denominator it will be 1 plus 1, 1 by 1 plus 1, 1 square means 1 half. So, 1 by root 2, that means 0.707 R in by Rs plus R in, that we get at frequency f is equal to FLC1. Now, if we consider the overall voltage gain AVS, because this was the ratio between Vi and Vs. Now, for the amplifier, let us consider what is the voltage gain V naught by Vi. V naught by Vi, because if we look into this amplifier circuit again, V naught is here, this is Vi. In between V naught and Vi there is nothing, no capacitance, only the circuit is just similar to the mid frequency region circuit. So, V naught and Vi, this ratio is same as the voltage gain V naught by Vi for the amplifier in the mid frequency region, and that is having the relation which is known to us. So, we know that we can replace that V naught by Vi, which is AV, that means the voltage gain, which is nothing but, if we consider the magnitude only, minus sign we are not writing, beta into RC parallel RL by beta plus 1 RE, that is the voltage gain between output terminals and input terminals. But now let us consider the overall voltage gain V naught by Vs, that can be written as by a chain rule. I can write it as V naught by Vi into Vi by Vs. Now, V naught by Vi is this one, AV, V naught by Vi is, we have found out Vi by Vs, and Vi by Vs is equal to this one, Vi by Vs equal to this expression AV into R in by Rs plus R in. This is the V naught by, this is V naught by Vi, which is AV, and this part is equal to Vi by Vs. So, writing this AV, we can just replace also AV, but keeping it as it is. Keeping it as it is, we are getting AV, which is the voltage gain V naught by Vi. So, this AV is nothing but V naught by Vi. Similarly, Vi by Vs, that was just now found out, which is from this R in by Rs plus R in into this part. That is what we are expressing, and we are considering magnitude, that is why I am writing only the magnitude part. Or I can write this V naught by Vs as AV as F, considering the frequency. So, now we can write it as A naught into 1 by 1 plus FLC1 by F whole square to the power half, because AV into R in by R in plus Rs, this is nothing but AVS, that is the mid frequency range overall voltage gain without considering capacitance. So, that is nothing but again A naught in the mid frequency region. So, mid frequency region voltage gain, if it is A naught, magnitude we are considering. Another part is there, which is 1 by 1 plus FLC1 by F whole square to the power root, to the power half or under root. Now, at frequency FLC1, when this F is equal to FLC1, this part becomes root 2. So, overall voltage gain AVSF is equal to 0.707 A naught, and that is the lower cutoff frequency FLC1 at which this happens. So, now the lower cutoff frequency due to C1 is equal to 1 by 2 pi Rs plus R in into C1, because at that frequency when you substitute F is FLC1 by this one and make F is equal to FLC1, then we get our required criterion that the voltage gain drops up to 0.707 times the mid frequency gain. So now this FLC1 or the lower cutoff frequency due to C1 is equal to 1 by 2 pi into Rs plus Rin into C1. So this lower cutoff frequency can be found out easily if we look into the circuit having this capacitance C1, look from this input side across this C1. If I find out what is the effective resistance, it is equal to Rs plus Rin. So Rs plus Rin is the effective resistance looking from the capacitor C1, of course by making Vs 0 when you find out effective resistance, and R effective into C1. Actually this whole term will be determining the time constant of this circuit having capacitance, and from that we can find out what is the frequency by 1 by 2 pi into R effective into C1. This is actually the lower cutoff frequency. So let us try one problem for finding out the lower cutoff frequency due to the capacitance Cs alone as shown in this figure. So in this example we will be finding out the lower cutoff frequency due to the capacitor Cs alone. So for solving this example we have to first of all draw the small signal model for this transistor amplifier. So the small signal model will be, as we discussed earlier, we will be having the capacitance in the high frequency and the low frequency region also. So let us draw the small signal model including the capacitances, because we are concerned with the frequency response, and as is the method for drawing the small signal model which we discussed earlier, let us proceed. So this circuit is having Rs, Vs is the source, Cs is the series capacitor with the source, and in the small signal model we know that the parallel combination of the biasing resistance R1 and R2, let us equivalently express it as Rb, and this is beta plus 1 Re, and Re is the capital E is the emitter resistance, C is the emitter bypass capacitor, and here the current source beta Ib, and the collector resistance Rc, and the collector capacitance, load resistance, all will be here. So here in this model, due to this Cs alone we will be finding out the lower cutoff frequency. Now replacing these values, we have to first of all find out what is Re, that we do not know. So in order to know Re, we have to be concerned about the DC equivalent circuit. So DC equivalent circuit, if we draw, then it will be having this R1 and R2 parallel, this is Rc, and this is the transistor emitter resistance R1, R2, VCC 20 volt, Rc is equal to 4 kilo ohm, and for this transistor beta value is given as 100. So in this example we have actually beta is given by 100, that we have to note beta value in order to find out the parameters. So Re value is 2 kilo ohm, R2 is 10 kilo ohm, R1 is 40 kilo ohm. So now what will be this R1 parallel R2, that is, let us write as RB. So, it is R1 R2 by R1 plus R2, and putting these values 40 into 10 by 40 plus 10, we get 8 kilo ohm. So, this is the value of the parallel equivalent resistance. So, the Thevenin's equivalent circuit will give us the value of Re, because we know that the Thevenin's equivalent circuit, if we draw replacing this RB, whatever we have got, which is 8 kilo ohm, this is VCC, RC 4 kilo ohm, VCC is equal to 20 volt, RE is equal to 2 kilo ohm, and we need to know the Thevenin's equivalent voltage. So, what is Thevenin's equivalent voltage? That can be found out from this V Thevenin equal to VCC into R2 by R1 plus R2. So, 20 into 10 by 10 plus 40. So, this equal to 4 volt. So, we can now replace here 4 volt. So, now we can find out what is the Re. This is IB, base current. So, in this circuit, V Thevenin minus IB RB minus VBE minus beta plus 1 IB into RE, that is equal to 0. So, replacing these values, 4 minus IB we do not know, RB is 8 minus 0.7 minus 100 plus 1 into IB into RE is 2 is equal to 0. So, this equation will be giving the value of IB. So, if we do this, we will be getting the value of IB as, you should check it and get a value of 0.0157 milliampere. So, this is the value of IB which we get from this equation. Solving this equation, we get a value of IB is equal to this much. So, now if we know IB, we can also know IE, which is nothing but beta plus 1 into IB. So, beta value is 100, 100 plus 1 into IB is 0.0157. This is in milliampere. So, what we will be getting is 1.586 milliampere. So, knowing the value of I, we can now find out what is the value of small re, that is, we know 26 millivolt by capital I capital E. So, putting these values, we get 26 millivolt by 1.586 milliampere, and that is equal to 16.39 ohm, because this order is millivolt by milliampere. So, it will be in ohm. So, 16.39 ohm is small r small e. So, beta plus 1 Re equal to 100 plus 1, that is 101 into 16.39, and that comes to 1.655 kilo ohm. This is ohm, but in kilo ohm we will be getting 1.655 kilo ohm. So, if we know now this beta plus 1 Re, then input resistance R in, if we look into the small signal model and find out what is the input resistance R in, we can find this out, that is equal to RB parallel beta plus 1 Re. So, in the mid band region, that is when we ignore this capacitance effects, that R in, the input resistance, we have to find out. So, that R in is equal to, we write mid band mid band. So Rin is equal to Rb parallel beta plus 1 Re. So replacing these values, Rb is equal to 8 kilo ohm and beta plus 1 Re we have found out to be 1.655. So 8 into 1.655 by 8 plus 1.655, that is equal to, we get 1.371 kilo ohm. So if we know this Rin in the mid band region, that is the input resistance for the mid band frequency region, then in order to find out the lower cutoff frequency, we know that we have just now found out that the lower cutoff frequency due to Cs alone. Individually we are finding out the lower cutoff frequency, and that we know FLCS if we denote, that is 1 by 2 pi into effective resistance as looked by this capacitance Cs, and that is nothing but Rs plus Rin into Cs, because the effective resistance as looked by the capacitor Cs, this is the capacitor Cs. So what will be the effective resistance? That is Rin plus Rs. From this side if we will be looking into, so it will be Rs plus this Rin. So what will be this value? That value we can find out FLCS equal to 1 by 2 pi into Rs series resistance here with the source is 1 kilo ohm. So 1 plus 1.371 that we have found out into the capacitance Cs, which is 10 microfarad, but this is in kilo ohm. So into 10 to the power 3 we have to do, into 10 to the power minus 6 into 10, that is 10 microfarad is the capacitance Cs. So if we do this calculation, then we will be getting the value of FLCS to be 6.71 Hertz. So this capacitance Cs is offering a lower cutoff frequency of 6.71 Hertz. So in order to know the lower cutoff frequency due to this capacitance, we have seen that we have to find out the effective resistance, which is by looking from the capacitor what effective resistance is there, and for finding that out we have seen that we have to find out the input resistance, that is in the mid band region, and that input resistance is found out by considering the small signal model, and after finding out that Rin, we found out the effective resistance because it is simply the series resistance between Rin and the Rs. So this effective resistance due to the Cs only, that has been obtained, which is equal to 1 plus 1.371 kilo ohm, and then it will be giving you the value of the lower cutoff frequency. So in this discussion we have today analyzed the transistor amplifier in the common emitter configuration, having the low frequency as well as we are considering first the low frequency, and then we will be also considering the high frequency analysis. But today we have discussed the lower cutoff and upper cutoff frequencies, and we are trying to find out what is the cutoff frequency value for both the lower and upper frequency regions, and for the lower frequency region we have found out the lower cutoff frequency considering one coupling capacitor C1. So, also we will be finding out next the lower cutoff frequency due to the other two capacitances, and then we will be also finding out the overall cutoff frequency in the low frequency region, and then also we will find out the higher or upper cutoff frequency.